Hello everybody. So now we are going to go through a quick review on the basic vector algebra or vector operations that we need to kind of remember when we go through the coming parts of this chapter. So the what we see here is the vector, and we know the vector is a quantity that has magnitude and direction, and this is different from scalar quantities, which has just magnitude without a direction. In fluid mechanics, there are a lot of vectors. There are the velocity is a vector, the force is a vector, the acceleration is a vector. So there are a lot of vectors that we deal with in fluid mechanics. So we express the vector with three components. In Cartesian coordinates, it's in the x, y, z directions. In the cylindrical coordinates, it's r, theta, and z. And for the spherical coordinates, it's r, theta, and phi. So it's something that is well known. So for any velocity, it will have three components based on the coordinate system that we deal with. So one other thing we need to remember about the vectors is the derivatives of the vectors. So there are two types of derivatives that we deal with. There is what we call the gradient of A. A is a vector, so it's the gradient is the derivative of this vector, and we give it a symbol of the nabla or del. This inverted delta is called nabla. And this converts the scalar quantity into a vector quantity. So if we have the gradient of A, or the nabla A, it's the derivative of A with respect to x in I direction plus the derivative of A with respect to y in j direction, which is xy direction, and the derivative of A with respect to z in k direction, which is z direction. We have the same thing in the spherical and the cylindrical coordinates, which is the same thing but in different coordinate system. So this is kind of a expression of the derivative of quantity. The other type of derivative that we deal with is the divergence of a vector, which is the same symbol, but it's a dot product. And for the dot product, it has to be between two vectors, so it's the derivative of a vector. So it's the difference between the gradient and the divergence, and then the gradient is the derivative of a scalar quantity, and the divergence is a derivative of a vector quantity. So use this dot product here between the del and the for divergence of A, or del dot A is the derivative of A with respect to x, plus the derivative of A or the component of A in x direction with respect to x, plus the derivative of the component of A in y direction with respect to y, and the same for z direction. So what we get here is a scalar quantity, so we'll have just one number at the end for this divergence. And of course this is the same for the cylindrical and spherical coordinates. Since this is the derivative in vector operations, the derivative rules apply to it. So if we have two multiplied vectors, let's say a, b, and we want to get the divergence of these two, so it's going to be like what we do in regular calculus. It's the derivative of the first multiplied by the second plus the derivative of the second multiplied by the first. So it's a del dot b plus b del dot a. So this is the derivative to multiplied vectors, which can be written this way. This a and b need to have a vector symbol above them. It's missing here. Okay, so anyway, so this is the derivative. There is one more kind of derivative. It's not as famous as the other two, and it's mostly used in fluid mechanics and the related fields like heat transfer and mass transfer, which is the total derivative. And to understand the total derivative, we need to take a step back and understand something about the derivatives that we have. Let's say we are doing a derivative of the anything, with the velocity, for instance. So when we do the derivative of velocity, we set our control volume, as we used to do for a lot of times before, and we say that there is mass in and mass out, and we do the accumulation is the difference between in and out, and this is what we have for the balance equation, and then we can do the integration. But anyways, the when we have the derivative is a regular derivative, that what we used before, we set the derivative on a specific volume in space. So we set this volume, which we used to do before, as a dotted region around the specific, or dotted loop around the specific region, and then we do the balance in and out, and we do all the things, or the balance equations on this volume in space. This is the regular derivatives, the divergence, or the gradient. Okay. But what we have here is what we call the total derivative. It's a different thing. For the total derivative, we are doing the derivative on a specific part of the fluid, and we are doing this derivative while the fluid is moving. So it's like we are tracking this part of the fluid as it's going from one place to another. So in this case, the derivative, you can consider it as a moving system. That we are not just focusing on part of space, we are focusing on part of the fluid, and we are tracking the fluid as it's going from a place to another. So this is the difference between the regular derivative and the total derivative, and that's why sometimes it's called material derivative, because we are focusing on a specific part, or specific part of this material. Okay. So it's the rate of change of the physical quantity, like velocity or temperature, experienced by an observer moving with the fluid. So it's like we're moving with the fluid and tracking it. And this is and why it's written like this. It's not just a regular time derivative, it's a time derivative plus the velocity multiplied by the or it's written like this, like u dot del u. Okay. So this is just to understand what we mean by total derivative. We're just going to see it once while we are doing the derivation in the next couple of videos. So I just want to give you a heads up and let you understand what we mean by this. Anyway, so there is one last thing I want to to mention here, which is something we will use a lot in the derivations that we are going to discuss next videos. Is the divergence theorem. So the divergence theorem is there is a long derivation for this theorem, and I'm not going to go through this. It's already in the textbook. If you're interested, you can check it yourself. But the main point of this is to unify the parameter that we're integrating with. So there are some equations or parts of the equation that will be integrating over the surface, which we have here as the control surface. So the integration is over the surface of the control volume, and there are some integrations that would be over the control volume. So we'll have something that is dA and something as dV, and it's much better to unify this these equations. So to have all of them as integrals with respect to the area, all integrals with respect to the volume. So this is why we have this divergence theorem. It's converting the area integral. If we have parameter g, let's say this g is velocity or anything, so any other parameter, so it's an integration of this velocity dot n. N is the normal the normal vector to the cross-section area. So this is the integral of g dot n dA. It's equal to the del dot g dV. So if we have a shape like this, we can convert it into a volume integral, as we will do later. So this is just why we use this theorem, just to unify the parameter we are integrating on, and this will be very helpful in simplifying the equations. So this is all for this video. So I'm going to stop here, and we will continue in the next video, and we'll start with the types of equation we're going to use, and then we will see the shapes of the equations, and we'll go through the derivation inshallah when we start next video. So I'll see you then inshallah. Goodbye.